show that we're less than the design loads. What is Hudson Yards for Tutor Perini? It's two projects in one. It's construction of the Gateway Tunnel extension for Amtrak. That's basically an Amtrak underneath the yards, and then a platform level for high-rise towers in the mall. There's 4 towers, 60 to 85 stories, and there's a retail business area in the center, 10 stories plus or minus high in the retail business center. The tunnel structural design was done by Parsons Brinkerhoff. The platform and overbuild structural design was done by Thornton Tomasetti. The crane engineering by Howard Shapiro and Associates. I just want to give a special shout out to them because some really unique crane things going on there. What are some of the design constructability challenges? Access. It's construction in an active railroad yard. Again, Hudson Yard stores trains for daily LIRR operations out of Penn Station. So there's a lot of outage requirements. A lot of our work gets done nights and weekends when it's not their peak rush hour. Some of the column foundations are in between yard tracks, so there's only 6 feet in between ties. And there's some of the columns come down and bear on the tunnel roof, and these loads are up to anywhere from 15,000 to 30,000 kips on several columns. In terms of the challenges, as a construction engineer, so design engineers are responsible for determining effects of equilibrium on the deflected shape of the structure. And for us, structures can mean anything from rebar cages, standees, single beams hanging from a crane, to incomplete, partially braced structures or structures during various states of demolition. Therefore, we use the AISC direct analysis method frequently. This requires reduced stiffness to account for partial yielding. We include fabrication tolerances in our models. We look at various stages of construction or demolition, the loads at those stages. Not all of the combinations and critical loads are really covered in the ASCE, design loads on structures, so we have to figure out what these are and make sure that we have all the combinations in the right place. A tool that we use, general rule of thumb, is we use shapes that are more square than deep to account for uncertain boundary conditions. And note that sometimes deflections control. It's not just about the stresses or the forces on the members. It's about getting them connected. And if too much deflection means you can't get the bolts connected, what's the point? So getting the deflection right with uncertain boundary conditions is a little bit tricky. You can't always use the charts in the back of the beam section of AISC. I'd also like to point out an example of a webinar that has covers a lot of these construction challenges. AISC has an excellent webinar where they give detailed examples of truss and beam erection calcs. They go through the amplification factors, things like that. It was done by Will Jacobs and Clint Rex of Stanley D. Lindsay and Associates out of Atlanta, and that's on the AISC website. If you remember, it's free. A little further on the challenges, the boundary conditions for construction engineers are not often the ones that were meant when they came up with the beam formulas and design and column curves in the manuals. So we have to be aware of the limitations of the formulas for what we do. An example of that is what is K if you're doing the effective length method of column design. I think very seldom in construction engineering do you actually have a K equals 1. So we use, again, we use the direct analysis method frequently, where we use other factors like programming in fabrication tolerances, reduce stiffness, to so that we can use a K equals 1. one of the basic challenges we have as construction engineers is equipment selection. An example of this is one crane versus two crane picks. With the one crane pick, when both slings are coming from a truss up to the crane hook, it's absolutely critical that the center of gravity of the member is known exactly. If you don't have the center of gravity in the right place and your sling is equally offset, the member will be lifted uneven, and your iron workers will have a really difficult time making the bolts. They will not be happy with you. Two crane picks. There's you can use two crane picks.
You're on the wrong screen. You can see your desktop.
Okay. I just switched my desktop. Hopefully you can see the slides a little bit better now. Back on the two crane
Russell.
picks. Yes.
Russell, you're on the other monitor. You're showing the Excel file. So switch it back to the monitor you used before, and then press F5.
F5.
Yeah.
Is the right screen now?
Nope. Or on the bottom right.
Yes.
Where you manage the screen resolution, there's like a presentation slide looking icon. You can click that. Nope,
No.
on the left.
Towards the left.
Yep, on the left. You know the plus minus button, and then on right next to it, you see like no, it's on the right. Yep. Left. No, go on left. Yeah, from there, go on left. Yes, no, left. Yes, that one.
There you go. How's that?
Oh no. Press ESC. Press ESC. Escape.
Yep.
Yeah, press escape. Oh yeah, click that one. Yes. Oh. No, press escape. Yeah, click one next to it. Left. Yes. There you go.
Okay, can you see my screen now?
Yes.
Okay. Should I continue?
Yep, go ahead.
Okay. So, sorry about that. A few technical things here. Here's an example of some user-defined properties with MIDAS Civil. Here's a normal steel properties, material properties on the left. And here's the user-defined properties on the right that account for reduced modulus elasticity, 0.8 times Z. If you can see it, it's 23,200 KSI. Next screen, sliding tower crane. Here's a good example of non-traditional design. This tower crane actually slides across this beam system with a push-pull jacking system. Other challenges specific to Hudson Yards. Shipping logistics. The A-frame columns and trusses have to be spliced on site. Design of assembly jigs to complete the assembly of the trusses and columns in the field. We use lifting lugs to pick up the trusses and columns, and these welds the welds on these lifting lugs that connect them to the columns have to be designed to resist bending. Concrete tunnel roof construction. That was something unique, 12 foot thick. Designing the rebar standees. When I thought about steel design and concrete design, I never really thought about having designed rebar stands, but when your roof is 12 foot thick and you have over 500 PSF walking across the top of it, these design of this stuff can be pretty critical. Another example is rebar cage installation, trying to pick up rebar cages that are assembled on the ground and setting them in the caissons. Some of them, I think Hudson Yards might have been 85 feet long. At City Island, we had one that was 110 feet long. And I think this is my MIDAS model of that, showing the deflection that we would get during erection. And this is actually the 110-foot cage being set into place. And again, you know, equilibrium on the deflected shape, right? It's can be a little bit tricky with some of these things that we don't always think about designing. Here's a 70-ton caisson core being set into place at Hudson Yards. I thought it might be interesting to show some slides on the construction of the tunnel. So here's basically the pre-construction photo. And this is utility relocation, always there at the start. Very big project, and there's always something that's a surprise, right? We're starting the secant wall construction with this slide. You can see the drill rigs getting in there to drill for the core columns. Next slide, we're just going a little further with that. And now we're starting to get down. You can see the tiebacks. This is the secant wall. Like all construction in New York City, you have to have some type of water barrier. So they went with the secant wall in this tunnel. Here's the tunnel excavation. You see we hit quite a bit of rock. This is the construction of the slab and the walls. A little further. And this is the roof. This is the 12-foot thick slab section I was talking about. And another shot of the roof construction. And here we are, finally backfilled. Getting into some of the stability of some of the members being erected. This is a plan elevation of a truss we had to set. This is the shop drawing of the truss, and you see one thing that's kind of interesting is these trusses are not symmetrical. You see there's no diagonal that goes back up from here to there. They're not all at the same angle. Here's another shot that kind of shows the lack of symmetry on these trusses. And here's a Tekla model. You can get the weight of get an idea of the weight of the individual pieces. This section weighed 88 kips. This section weighed 99 kips. And this section 62. The columns are about 61 kips. So for erection stability, I talked about the fabrication tolerances. The maximum fabrication tolerances per AISC is 1/8 of an inch times total length in feet divided by 10. Applied wind loads, we use 50 PSF per ash toe. Here's a MIDAS model of one of the trusses. This is kind of a diagram that kind of shows the different cases for sweeping the top and bottom chords. Case 1, the top and bottom chords are swept in the same direction. Case 2, they're swept in opposite directions. This is the axial forces in the top chord for case 1. Bending moments due to wind loads, case 1. And the truss forces, case 1. Here's case 1 deflection. These are my calcs. And one of the things I like about MIDAS is, you see up here, there's a KLO over R of 356.4. Other programs will see that that's more than what is allowed and just knock out of the box and not give you a code check. But with MIDAS, they will continue the calcs and tell you what it would be. They just give you that warning. So here, we're about 65% capacity on the top chord with the wind loads. And that's a handy feature to have. This was case 2. And I think we were a little bit different in the way that the controlling condition was when both were swept in the same direction. I know other people have done it, and it's when they're swept in opposite directions. But these members were huge, W14 by 342s, or W14 by 500s in the top chords. This is, throw a couple slides into some of the trusses being erected. This is the F-line truss. This is the node, the column. They call it the node because everything kind of comes together here. And if you notice here, it looks like a truss warehouse. See the trusses on top of the other trusses? This is where we assembled them. So they would come in, be delivered to the job site in pieces, say 2 or 3 pieces, and we had a jig up here where we spliced them together. You can see the beams that stick out, and we had chain binders to hold them erect when they were making the splices. Here's a close up. Here's a picture of the chain binder holding it in case of heavy winds. And this is from my calculations. This was my preliminary sketch of the assembly jig. Here were the trusses they're setting on. This is the beam that goes across, and these are the trusses being assembled up on top. Talk a little bit about checking stability after erection. Now, if you can see here, this is the D truss again, the D-line truss. And this truss there's only one truss on one side of the column at this point. In the final design, you have a truss on each side of the column. But at this point, there's only a truss on this side. So you can imagine the load on these anchor bolts here, especially when you put 100-mile-an-hour wind on this truss, are pretty big. So you can see the braces. I think we had 4 or 5 at this point. Here's the MIDAS model of the truss on one side of the columns with a 100-mile-an-hour wind load. This is now we've got the other side set, and both sides were erect. I think we only needed 3 braces at this point. The MIDAS model with that, I think we went from 462 foot kips a moment with one side set, and down to 159 kip feet with both sets. So talk a little bit about the A-frame columns. They're one of the unique features of Hudson Yards. It's basically one column supported by 2 caissons. I talked about the 6-foot clearance in between ties. That means the largest caisson can be about 5 foot diameter. So basically, it's they split it between 2 caissons, the column load between 2 caissons. So here's the bottom half of column B15. Here's the top half. Here's the upper section. And here is here's the assembly jig up on, this is 33rd Street. And this is where they're splicing the top and bottom of the columns together. Here is us picking up the bottom section to set it into the jig, and I talked a little bit about bending on the welds, and you can see that clearly these lugs are going to have some bending on them. Next shot, we're picking it up now, it's straight. I also want to point out that we use snatch blocks quite a bit to allow the load transfer between lift points as the column goes from horizontal to vertical. That allows an equal distribution between these 2 lugs. And this is column E14 set in place. In its position, you can see the splice where the columns where the full pen welds are made, splicing the top of the column to the bottom. Here's 33rd Street. This is the jig from down there. This is about 30 feet. Had to submit a lot of calculations on the retaining wall to DOB to show that we weren't going to knock it over when we put the trusses together. Just point out, a lot of these columns weigh between, say, 150 and 250 kips. So we get 6 of them up there, you know, that's about 750 kips. Here's a slide showing the full penetration weld in progress. You see the heat blankets to heat up the steel, part of our welding process. Here's some of the lugs that you see for lifting the columns into place. We put them on top of the sections, and let's see. Here's a picture of a column being lifted with it. It's there's the lug up there. One of the issues with these lugs is that the center of gravity of these columns, you can see, is not right in the middle of the member. So we really had to design these things offset a little bit. Here it is being lowered in its final position. Here is the MIDAS model of that. Another view of the MIDAS model. Here is my bolts on the top lug plate when the column is horizontal, my bolt calculations. Here's actually my calculations for the ability of the weld to resist bending. Here is, I thought I'd include a slide of the properties of a weld treat as a line. Basically, we use a unit length, and then we come up with a minimum weld size. Here is the bolt calcs for the upper section, and here's some pictures of a few of the columns in place. These are the laminated. These columns are called laminated columns. Basically, 4-inch plates, full pin welded together. Here is another shot of a lug, and you can tell that it's quite offset. Also, we put stabilizer plates in just in case there was some side load that we wouldn't get any buckling. Talk a little bit about 11th Avenue Bridge. This is, we do quite a bit of work on the 11th Avenue Bridge for the tunnel extension. The Amtrak tunnel runs roughly through the bridge about this, right around here. And if we look at that from the ground, let's say this is the pier. What we have to do is we have to temporarily support the bridge, say over here, put a temporary support in, a temporary beam in, so they can demolish the pier, build the tunnel, and then reconstruct a new pier for the bridge on top of the tunnel roof. So in order to facilitate the tunnel construction, we had to design used a box beam to support this bridge during the tunnel extension. Here's the MIDAS model of that section of the bridge. Here's a temporary support girder. A couple more shots of that. Here's this is my composite design check for the members up above to show that they're still good with the revised support location. One of the things I like best about MIDAS is the composite section check, the code check. These are the section properties. Here is my short-term moment. This is the moment that we get through the time the deck is poured. This is the moment that comes from the vehicles and the lane load and the construction equipment. Here's the calc for the yield moments on the top and bottom flanges. You can see this is the moment from the pouring the deck, and then the code requires us to see what additional moment we're allowed. In this case, the bottom flange controlled. Bearings. I modeled the rocker bearings with MIDAS Civil. The box girder sits on the rocker bearings. That's how we're going to support it while we're doing the construction. Here's a shot of the bearing extended. Here is the solid stresses on the bearing. This is the stiffeners. There were plates. And to support the one side, we have two 80-foot deep caissons I modeled and designed with the help of MIDAS. A lot of times we're going to have to put a crane on the bridge during the construction, and if I thought I'd have a slide of how we get the loads. This is from Bay Crane. This is an example of an outrigger load printout. So the number in parentheses is the maximum outrigger load that we have when we do this pick. In this case, the pick is 15,600 pounds at a 70-foot radius, 98.6 feet of boom, and a boom height of 74.3 feet. If we use a crawler crane, here's a printout from Manitowoc ground bearing pressure estimator. Just mind you that you see these PSI, you have to multiply it by the contact width tread of the crawler to get the full load. So Our crane is down here. These are my lane loads. These are my factored HS20 loads. They include multiple presence factors and impact, so if the numbers don't look normal, that's why. Here's my crane outrigger loads. I have a 108.1 kith outrigger over the front outriggers. I'm not going to be able to set that anywhere in here and make it work, obviously. The 58.3, I have a pretty good chance of getting that to work. So we set the outriggers right over the pier. And this is the printout of the composite section. I won't go through that again. Bridge deck demolition. Included a section of the bridge. We have to demolish part of the bridge for this. This is a model that shows the section of the bridge to be demolished. These are the overhang brackets, the standard Dayton Superior brackets. This is timber shoring in between the girders. For timber design, I use the UserDefined function here. I've put in section properties for timber planks under UserDefined Properties. Here's my loading. This is by contract. I think it's 100 PSF and a 2,000-pound point load spaced out over a certain area. And so based on my bracket spacing, here's the load on my bracket. This is the MIDAS model of the loading. Here's my bending stresses on my planks. Here's, I modeled the diagonal of the overhang brackets as truss members because they really can't handle any bending. So axial load only, please. Here's the top part of the overhang bracket and the post. Another shot of the loads on the decking. I guess that's it for Hudson Yards. We'll talk about the Harlem River Lift Bridge now. It's an access for Metro North trains into New York City, Grand Central Terminal. It's a critical bridge for Metro North. 2 side-by-side lift spans. We had a job, this was out of the New York Times, to replace the wire ropes that lift the bridge. It started as electrical upgrades. I'll show you in a minute. And then the wire rope was added. The wire rope replacement was added, and then I had designed a work platform that sat on the top of the bridge to facilitate the wire rope replacement. This is a photo of a bridge in better times. This is actually what caused the project, or what started the project. It was the fender system caught on fire due to electrical malfunction, and this is why they had to replace the electrical equipment. Here's the CAD drawings of my work platform. This is our erection plan. In plan view, we put a large crane on a barge down here, and there was a large Manitowoc, and we lifted the platforms into place during a nighttime outage. Here's an elevation view of our work platform. Quite a bit to work around. There's a wire up in here, a signal wire, that we really had to be careful of setting these things in place. Here's my MIDAS model of the work platform, my main member moments. I was asked to check the bridge for railroad loading and with the weight of the platform. So this is a Cooper E80 layout. I'm sure everybody recognizes that. When I look at the results of the Cooper E80, I came out with 2019 kits of compression, the end diagonals, which was about 20.1 KSI, which for a bridge built in the 40s, that was a little bit higher than what we wanted. I was about 80% capacity, and I wanted to be absolutely sure we weren't going to have issues. So one of the things I did to double check, reality check, was I took the actual equipment loads from Metro North equipment. I took this is an example of one of them. I'm not sure if this one controlled or not, but this was a Genesis locomotive with an M4 car, and you can see that their loads are quite a bit less than Cooper E80. And this bridge really doesn't see Cooper E80. This is the load from my platform. I had 110 kips here, 50 kips here. And with the equipment loads, the actual equipment loads, it wound up being about 980 kips versus the 2,000. And I was about 40% capacity, and I think everybody felt a little bit better about that. Here's a slide of successful completion. Here they're testing it. Our work is done, replacing the wire ropes, and we're lifting the span up. I was asked to give, I guess, a seminar, a quick 20-minute seminar on why Tutor Perini chose MIDAS. One of the slides I wanted to have was something to kind of break it up. So why did we choose MIDAS to avoid this? Seriously, we had some bridges in Connecticut. We had about 60 bridges, curved girders. We had to submit calculations to Designer and CDOT. There were some modeling issues with the program we were using at the time and deflection issues. And we wanted to put cranes on the new bridge decks because of the access restrictions with the job. The challenge is a huge amount of traffic volume in this area. If you've ever driven through New Haven, the I-95, I-91 interchange, a lot of access limitations. So we couldn't get access to just set every diaphragm in place. So we put the diaphragms at 60 feet so that we could set the big girders in place under the main outage and then come back with smaller equipment and set the diaphragms in place. Had to design shoring towers, overhang brackets, etc. Here's a photo of one of the bridges. Here is the MIDAS model of that bridge. Here's the MIDAS model of the falsework towers. And here they are in an actual photo. This is my progression of how we modeled it. And the bottom line is we came to the conclusion that our falsework tower was really not based on any stresses on the member. The members had plenty of capacity. But we were limited by the amount of deflection that we could have and still get the girders connected. Remember the curve, so they were kind of deflecting away from each other. So we came up with a ½ inch is the limit, and so that controlled our falsework spacing. The maximum overhang was 60 foot, which gave us about a ½ inch deflection. Falsework, these are just falsework calculations. Another photo of the bridge. This is another bridge on the project, the approach bridge. More falsework. I guess talk a little bit about East End access. We did a supportive excavation at Sunnyside Yards, a bridge. The technical name was ML4. And the challenge for this was we couldn't get in there and drive any of the standard soldier piles, sheet piles that we do and put tiebacks under here. The railroad tracks are right up here. And so the way it came out that we actually did this was we hand dug these piles in. Something that hadn't been done probably in a couple thousand years, right? We used liner plate. We put it right next to the ties up here. And we hand dug a big hole down, set these piles and these beams into place, the columns into place, and then I backfilled with K-Crete, flowable fill. And then so this end is the bottom of these columns comes down on top of the footing. Now the footing for this abutment extends all the way back here, so these three soldier piles all bear on concrete. So they have no embedment resisting capability. So what we did over here was we used concrete anchors to hold the whaler in here. We wound up using a couple rakers on this soldier pile here, and this side of the SOE was held in place with concrete deadmen up here in the embankment. So what we had with this SOE was a flexible system over here and a rigid system over here. So I had to come up with a way to keep these concrete anchors from being side-loaded, so I designed expansion joints for these whalers. And I'll show you some pictures as we go through. Here it is. They're basically two WT sections. There's the whaler in there, and you can see a little bit, there's just a section in here that keeps the whaler from backing out. It holds it in place, but the whaler can slide back and forth this way. Here's a raker system that helps hold this pile in place. You can see what we have to do is they're adding onto the bridge, so we're extending this abutment, say, towards us here. And so this wing wall had to be demolished. There's the liner plate. They're removing it as they go, but you can see the top of it here. Here's a trench box for setting the heel block for the raker. Here's the wing wall, a little bit more of the wing wall demolition. And starting to work our way down. There's tracks down here too, so we had Amtrak down here, and we had a Long Island Railroad up there. Excavations progressing. You can see just how close the trains are to our shoring system. This is a view from the top. It's a pretty deep cut. This is a view of the concrete anchors. It's a close-up, so you don't think the concrete anchor is supporting the whaler. There's a bracket here that actually has the load of the dead weight of the whaler. I don't want you to think I put it on the concrete anchors. Here's our reinforcement cage for the heel block. Here we have, we're starting to work the excavation down a little bit more. You can see where the wing wall is demolished. They're working on removing the liner plate as they go down. Just continuing to go. Here the wing wall is almost all gone. We've added the second raker. This is a shot from across the street. Here they are, a close-up of them removing the liner plate. This is what they actually dug the hole to set the piles in. This is the final depth. We're at subgrade here. At this point, we're going to backfill and start to come up for the footing. The next slide, I think it shows it. Yeah, here we backfilled. Here's the layout for the caissons to support the abutment extension. And that was pretty interesting. This next series of slides gets into where you had to put a crane on the roof of a building. It's actually, this building is anywhere between 5 and 7 stories deep. But the caveat is that the top floor is at ground level. So I guess no one would think about putting a crawler crane on a 7-story building if the top of the building was 100 feet above the ground. But when the ground is, the top floor of your building is at ground level, then all of a sudden putting a crane up there doesn't seem like such a crazy idea, I guess. So we had to put the crane up here, and these are struts to hold the story wall, the excavation support system. Here's another shot of where we're putting the crane, this area up in here. This is a shot of the building where it's basically the construction isn't completed. These are the struts to hold up the story wall. This is another shot of that area. You see the formwork, they're getting ready to form up the deck. You can see we support a subway system with this story wall. And this is another actually construction project over here. Here is a shot of just to show a very active subway line. And this is a shot from a distance. The crane is going up here. Basically, we take the crawler crane loads, as I showed before, from the ground bearing pressure from the Manitowoc, and we put it on dunnage, spread it across the roof, and there were certain sections where we can sit and certain sections where we can't. I think that pretty much covers the crane on the roof.